Okay, welcome back to the ChemDoctor, and this video is going to be the second in the series that deals with deriving a pH curve during the process of carrying out a strong base, weak acid titration. In the first video, what we did was we established the first 3 points on this graph. So we established the pH of the weak acid solution before any hydroxide was added. We established the pH of the solution where enough hydroxide had been added so that the concentration of HA is equal to A minus, and we also calculated the pH of the equivalence point being the place where enough hydroxide has been added to completely react with all 0.002 moles of the initial input of the weak acid, producing 0.002 moles of the conjugate base acetate, where acetate then at the equivalence point is the only molecule that is controlling the pH. So we established the pH of the equivalence point, the pH of the solution where HA is equal to A minus, and the pH of the solution that exists before the experiment is started, where only HA is present in the solution. Now what we're going to do is we're going to fill in 3 other points on this graph. We'll establish or derive the entire pH curve for this kind of titration, and we'll talk about what each of the regions in the graph means. Alright, so what we're going to do first is we're going to fill in a point that's going to be between 0 NaOH added and the 10 milliliter point, which is where HA is equal to A minus. So we're going to find the concentration of HA and A minus after adding 5 milliliters of sodium hydroxide solution. All right, and 5 milliliters of sodium hydroxide solution is the same as saying that we're going to add 0.0005 moles of hydroxide. So to figure out the concentration of HA and A minus, what we're going to do first is we're going to take and we're going to subtract the amount of hydroxide from the original amount of HA in the solution. So after the 0.0005 moles of hydroxide reacts with HA, that's going to leave us with 0.0015 moles of HA. And it's going to leave us with, it will produce 0.0005 moles of A minus. Now, we need to find the concentration of both the HA and the A minus. So we're now going to divide by the new volume. Now we added 5 mils to an original volume of 20. So now we're going to be dividing by 0.025 liters in each case. All right, so the molarity of the new molarity of our HA solution is going to be 0.06 molar, and the molarity of the A minus solution is going to be 0.02 molar. Okay, now to find the new equilibrium position, we're going to have HA, all right, is in equilibrium with H3O plus A minus. And our initial concentration of the acid is 0.06. The initial concentration of A minus is 0.02. All right, and we have 0 of H3O plus. We allow this to come to equilibrium. And the HA is going to decrease by X, the H3O plus is going to increase by X, and the A minus will be plus X. So now plugging in, we're going to have X times 0.02, okay, divided by 0.06, and this is equal to the equilibrium constant, 1.8, times 10 to the minus fifth. So my X value, which is also the concentration of H plus, is going to equal 5.4 times 10 to the minus fifth. All right. The pH, therefore, taking minus the log of this value, is going to equal 4.3. So I'm going to come in here now and we'll add our new point. I'll just run this line kind of up like that. Now we're going to, so this new point is going to be just under the 4.5 mark. So it's going to be approximately right here. All right. Now, what we're going to do next is find the 15 mil point. All right. And we find that exactly the same way. So in this case, we're taking 0.002 moles of the HA, and we're subtracting from that 0.0015 moles of the OH minus, and that's going to leave us with 5 times 10 to the minus fourth moles of HA, and we will end up with actually the same amount, so 0.0015 moles of the A minus. Now I'm going to leave it to the viewer to calculate the molarity of this, of each one of these things, and to complete the equilibrium reaction like we did in schematic number 1 here. And I'm going to go right for the throat. The pH of this solution after running the equilibrium calculation is 5.23. All right, and we can add that point in here now. So it's going to be, here's my pH 5 coming across here, and it's going to be a little bit above that. So I'll make my mark here. And you can see what's happening with the graph. All right, it's going to have like an inverted S right here, and then we have an S curve like that. So let's find our last point, and you can see right away that if we subtract from HA the amount of hydroxide we have at 25 mils, that we're going to end up with the main species left in the reaction is going to be 0.0005 moles of hydroxide. So we're above the equivalence point now. So to find the pH, we're going to take the pOH first of the hydroxide, because this is the sole producer of pH at this point. All right, where the only other thing in solution that can alter pH is the acetate ion, and we already talked about the fact in video number 1 that the hydroxide is a much stronger base than acetate, and therefore this is the guy that's going to produce your pH. All right, so the hydroxide pOH is going to be 1.96, and that means that the pH, when we take 14, subtract 1.96, the pH is going to be approximately 12, which I need to add that point up here. So we're going to have 12 here. All right, and coming across to 25, roughly just coming up. All right, our pH 12 is going to be about right in here. All right, so now what I'm going to do is I'm going to go ahead and establish the curve as best I can. My artwork might not be that pretty, but here's what the curve is going to look like. All right, so this is what the curve is going to look like. Now, let's go ahead and label. We're going to label what each of these regions mean. I'm going to move this 2.87 out of here. All right, and instead I'm going to put into words the situations here. So this point right here, all right, is concentration HA via pH with no hydroxide added. No hydroxide added. This point right here is where we have HA equal to the concentration of A minus. All right. Now, all right. I'll just finish labeling things, and then I'll come back to this, to the meaning issue. Now, let me clean this up a little bit here so it's easier to read. All right. Now, the equivalence point. Okay, so this point here is equivalence. All right, and this contains 100% A minus. So this determines pH. So the pH of your equivalence is given by the conjugate base and the Kb value. All right, the pH of the starting point is given by the concentration of HA and a Ka value. All right, it's important that you realize that in this part of the curve up here, that the pH is given by the concentration of hydroxide, because beyond the equivalence, the major species that's now in solution is in fact hydroxide, because you've continued to add NaOH into this collection flask past the equivalence point, past the point where there is any acetic acid left in the solution to react with the base. So the base at this point is solely producing the pH of the solution. All right, now I want to come back to the midpoint of this line in here. All right, the place where your HA is equal to A minus. This represents a solution we call a buffer. All right, and I'm not going to write this completely out, so you're going to have to listen carefully to my words. A buffer solution is a solution that resists changes in pH when small amounts of either hydroxide or hydronium are added to that solution. Number one. Number two, the buffer solution must contain quantitative amounts of both HA and A minus, and that's the situation you have across this part of the graph. All right, and I'm going to define this better. So when I say this part of the graph, I'm saying from approximately right in here to approximately right in here, this whole gap, this whole part of our curve is a buffer. And you're going to have buffers that always exist in a strong base, weak acid titration, or the flip side of that coin is a weak base, strong acid titration. Both classes of titrations will have a buffer zone within the pH curve where small additions of H plus and OH minus result in little, if any, change of pH. And you can see that for yourself as the blue line cuts across here. There's very little change in pH value for addition of NaOH. Now, the two lines that I drew here from one side to the other is what we call the buffer capacity. Let me clean that up a little, and we'll come down here like this and do the same thing. So this gap is my buffer capacity. And basically, from this midpoint, the buffer capacity of a given solution is going to make up a gap, which is essentially one pH unit to either side of this midpoint. One pH unit essentially to either side of the midpoint of this graph. Now, the other major issue you need to understand about this, that your professor or teacher are going to expect you to realize, is that if we know this point on the graph, if we can find this point, then we can know the Ka for this weak acid, because basically all you need to do is come straight across here to your pH, whatever that is, back calculate to concentration of H3O plus, and remember that at this unique point where Ka is equal to concentration of H plus times A minus over HA, you can see at this midpoint that the concentration of A minus cancels with HA, and the Ka of the acid is going to equal the concentration of H plus at this midpoint. The significance of that is that if we have a graph and you can extrapolate to the line over here and find the pH, you can back calculate the H plus, and if you know the H plus, you know the Ka for that weak acid. Okay, and with that, I'm going to go ahead and close this video.